Women in Data Science Worldwide has been around since 2015. We started pretty small, as just one conference on Stanford campus, and our aim then was to simply feature outstanding women doing outstanding work in data science. And then we grew. We grew into a global movement, connecting women and also men around the world.
WIDS has grown organically, responding to what the needs of the community are, what women data scientists need, and exploring new ways to interact. Stanford University is proud to have been the birthplace of WIDS and a decade of growth. With our unique strength in data science, computation, and AI, Stanford was the ideal incubator to support this force for advancing diversity in data science. WIDS has had a lasting impact on data science at Stanford, with a co-founder of WIDS as a founding member of Stanford Data Science. Including multiple perspectives is baked into the core identity of our programs.
It's critical, and we need women in these roles. Every individual brings their own perspective, and so we need to make sure the entire workforce is represented.
Because it really fosters that sort of community building you want when it comes to not just data science, but really any, I think, efforts to try and engage more girls and women.
So the fairness mission that we have is really try to enable that two people with equal talent should have an equal shot at opportunities.
I also just encourage people not to give up and keep arguing for what you believe in and what's important to you and what you think will make a difference.
WIDS is about the sense of urgency we should all feel to ensure that women earn that seat at the table based on their skills and talent across the world.
WIDS has inspired me to believe that more is always possible.
WIDS has inspired me to think big. WIDS has inspired me to learn more.
It brings together some of the leading scientists in the world.
The journey is just beginning. At WIDS, we're not just envisioning a more inclusive future in data science and AI, we're making it happen. From equipping students with critical skills to advancing career development, we're expanding access to education, mentorship, and empowering support for tangible impact. The next decade starts now, with action, with us. Join us in shaping the future. Volunteer, mentor, or donate today.
السلام عليكم ورحمة الله وبركاته. السادة الحضور الكرام، المتحدثات المتميزات والمشاركون الأعزاء، يسرني أن أرحب بكم جميعاً في ملتقى المرأة في علم البيانات 2025 هنا من الباحة. هذا الحدث يمثل فرصة ثمينة لتبادل الأفكار واستكشاف الابتكارات ومواجهة التحديات التي نواجهها في مجال علم البيانات، الذي يشهد تطوراً متسارعاً ومستمراً. إن العالم اليوم يعتمد بشكل كبير على البيانات، حيث تلعب دوراً محورياً في اتخاذ القرارات في مختلف جوانب الحياة، من الصحة إلى التعليم وصولاً إلى الاقتصاد. إلا أن البيانات ليست مجرد مورد قيم، بل تطرح أيضاً تحديات معقدة خاصة مع انتشار المعلومات على المنصات الرقمية. يصبح من الضروري حينئذ استكشاف التطورات الحديثة في علم البيانات، عالية الأداء وقواعد البيانات الغير العلائقية. يأتي ملتقى اليوم في إطار سلسلة ملتقيات المرأة في علم البيانات التي تنظمها منطقة الباحة وتديرها السفيرتان الدكتورة أحلام النابلي والدكتورة سونيا اللجمي. أنا دكتورة أحلام أدير حوارات جلسات اليوم، وهذه السنة الثانية لي كسفيرة في علم البيانات بمنطقة الباحة. يسرنا في إطار فعاليات ويدز أن نقدم لكم هذه الجلسة المتميزة التي تسلط الضوء على أحدث التطورات في علم البيانات عالية الأداء وقواعد البيانات غير العلائقية، وذلك بمشاركة نخبة من الباحثات المتخصصات اللواتي قدمن إسهامات بحثية نوعية في هذا المجال. وما نقدمه اليوم هو ناتج تعاون بحثي بيني وبين المتحدثات في المحور الأول. يشتمل البرنامج اليوم على مجموعة من المحاور المهمة التي تسلط الضوء على أحدث التطورات في مجال علوم البيانات والذكاء الاصطناعي. يبدأ البرنامج بمحور إعادة تصور ذكاء البيانات الذي يستعرض الابتكارات في قواعد البيانات غير العلائقية NoSQL. يليه محور الجيل الجديد في علوم البيانات الذي يبرز دور الحوسبة المتقدمة في تسريع التحليل والابتكار. تسهم هذه الابتكارات في تمكين تحليل كمية هائلة من البيانات المتنوعة بسرعة وكفاءة، مما يعزز من قدرات البحث واتخاذ القرارات في مختلف المجالات العلمية والصناعية. يشهد عالم قواعد البيانات غير العلائقية تحولاً جذرياً في أساليب إدارة البيانات وتحليلها، بما يواكب التوسع الكبير في حجم البيانات وتنوع مصادرها. ويهدف هذا المحور إلى إعادة تصور ذكاء البيانات من خلال تقديم إطار جبري متكامل لقواعد البيانات الوثائقية يتيح توسيع وظائف التحليل المتعدد الأبعاد OLAP لتشمل البيانات الغير المهيكلة، ويسمح هذا الإطار بتنفيذ تحليلات معقدة بمرونة أعلى ودقة أكبر، مما يمكن المؤسسات من استثمار البيانات الحديثة بكفاءة أكبر. وانطلاقاً من هذا الأساس النظري الذي يقدمه الجبر الوثائقي، تظهر الحاجة إلى منهجيات تطبيقية تعزز القدرة على تحويل هذه المفاهيم إلى أدوات عملية. ومن هنا تأتي أهمية تطوير قدرات التحليل OLAP وعمليات الاستخلاص والتحويل والتحميل لتتلائم مع طبيعة البيانات الوثائقية. ويسهم هذا التطوير في تحسين جودة البيانات وبناء مخازن بيانات أكثر توافقاً مع متطلبات NoSQL، بما يعزز توحيد الرؤية بين الجانب النظري والتطبيقي لذكاء البيانات المعاصر. المداخلة الأولى بعنوان Extending OLAP Capabilities to NoSQL, a Comprehensive Algebra for Document Databases، تقدمها الدكتورة سمية، تطرح فيها رؤية بحثية متقدمة حول كيفية نقل قدرات التحليل المتعدد الأبعاد. ومن خلال هذه المداخلة سوف تقدم الدكتورة عرض جبر شامل يسمح بتمكين التحليل الهيكلي حتى في غياب البناء التقليدية، مما يفتح المجال لتطبيقات ذكاء البيانات على بيانات غير منظمة وموزعة. تفضلي دكتورة سمية.
السلام عليكم. شكرا دكتورة أحلام. I'm so excited to be one of this year's edition of the Women in Data Science series. And I would like to thank you again for the invitation. Well, in fact, today's presentation, as you mentioned, is entitled Extending OLAP Capabilities to NoSQL, a Comprehensive Algebra for Document Databases. In fact, in this presentation, I share with you how we're solving one of the biggest challenges in modern data analytics, bringing together reliable OLAP capabilities to the flexible world of NoSQL databases. Actually, this presentation is based on our research paper entitled Formal Algebra for Document-Oriented NoSQL Databases Formalization and Evaluation, which was recently published in the prestigious Q1 journal Cluster Computing. This work is a collaboration between Dr. Sondaba Aziz, myself, and Dr. Ahlam Nabli. Okay, we can get back to the agenda of the presentation. Over the next 20 minutes, we'll embark on a journey from introducing NoSQL data warehouses to understanding why traditional approaches are failing us, and introducing then the spectrum of solutions from workarounds to a foundational fix. Hence, this presentation is composed of four main sections. The first one is the context, which represent the new paradigm of NoSQL data warehouses. The second section will be the core problem. The third, we will present the solution spectrum. And finally, we will conclude this presentation and we will open the discussion for further questions. All right, let's begin with the context and motivation to frame our presentation. We're now flooded with data that is anything but structured. Picture this, like we're trying to fit the explosive messy reality of modern data You can think of social media feeds to IoT sensor streams, the ever-changing user profile, and so on, into the real neat, rigid boxes of traditional databases. In fact, it's just like trying to pour the ocean into a swimming pool, right? So this shift isn't a gentle evolution. It represents a fundamental paradigm shift in the very nature of the data we must process and analyze. And certainly, our traditional relational data warehouses are hitting a wall when trying to handle it efficiently. So the fundamental mismatch is why we need a completely new approach to data warehousing. So what's the alternative, right? Imagine a data stream that grows with you effortlessly, that adapts to your changing needs, and that never goes down. That's the promise of NoSQL data warehouses. All right, let us first formally define the concept of NoSQL data warehouses. In fact, it's a distributed data management system designed specifically for online analytical processing of the complex and versatile data types that define the modern digital world. This architecture is fundamentally built upon three core principles. The first is schemaless design. The second is the horizontal scalability, and the third is the high availability. Now, high availability means that the data is automatically replicated across nodes, ensuring that the system remains operational and accessible even if individual component fails. As we transition from theory to implementation, extensive research demonstrates how the NoSQL data warehouse paradigm is realized across different database technologies. It is crucial to understand that the foundation of the NoSQL data warehouse is just a standard NoSQL database, such as MongoDB or Cassandra, and which provides the scalable and flexible storage substrate. On top of this foundation, we implement the specific logic for data warehousing. We define facts, dimension, and managing the pre-aggregations to enable efficient OLAP queries. Now, document-oriented databases like MongoDB provide the ideal foundation for modern data warehouse due to their JSON format that it naturally mirror real-world data structure. As we started building these new systems, we discovered that the very flexibility that made them so attractive for storage was creating a nightmare for analysis, which brings us to the core problem: flexibility at a cost. The very feature that makes NoSQL powerful is in fact creating its greatest analytical challenge. So we now see the fundamental tension. Schemaless flexibility in storage creates analytical chaos. Consider a user profile collection. Documents can have completely different structure, some with nested preferences, other with flat fields, and other with missing data entirely. This means a simple query like counting active user can yield wildly different results. Like a registration date field, for example, it may be a date in some documents and a string in others, or missing altogether, silently correcting any trends of analysis. This structural chaos creates a ripple effect at the query level because documents can have widely different structure. Even the same analytical operation requires completely different implementation. Now, a simple rollup by continent, for example, may need a basic grouping for flat documents, but require complex unwinding and navigation for nested structures. This means analysts spend more time wrestling with the document navigation than actually solving the business problem itself. This fragmentation means that we can develop universal optimization strategies. In fact, here is each query for each structure in each database become a custom optimization challenge. Right. This leaves every data team asking the same desperate, set of questions. How can we trust our analytics when the foundations keep shifting? And are we making million-dollar decisions based on incomplete or inconsistent data? And most importantly, is there a way out of this mess that doesn't mean giving up on NoSQL benefit? Right. Now, the industry hasn't been sitting idle, right? We've seen various attempts to solve this, but they all feel like putting band-aids on a broken leg. Right, let me explain what I mean by that. Current solutions only provide partial fixes. Some of these solutions include polyglot persistence, materialized views, schema-on-read approaches, and strict schema enforcement. All right, let's present each of these solutions in more details. The first solution depicts using a dedicated OLAP engine. Now, this approach is what I call the architectural workaround. Instead of solving OLAP within NoSQL itself, teams simply bypass the whole problem by introducing a dedicated analytical database like Snowflakes or ClickHouse into their architecture. Here's how it works. The application still uses NoSQL database for its operational workloads, but then through complex ETL pipelines, they extract the transform and load the data into separate systems specifically designed for analytics. Now, this doesn't solve the NoSQL OLAP problem. We're essentially admitting that our NoSQL database cannot handle analytics, so we built an entire parallel infrastructure to compensate that. All right, the second solution is enforcing a strict schema. This solution is perhaps the most ironic one. To achieve analytical consistency, we give up on the very flexibility that led us to choose a NoSQL system. It is a classic case of using database validation rules or application level to enforce a fixed schema on the collection of documents. The third solution, which is in this slide, is the schema-on-read approach. Now, it imposes a structure when querying raw data. While flexible, it merely shifts the problem to external engine. We're still relying on SQL rather than creating a native NoSQL solution. The fourth solution here is materialized views and pre-aggregation. Now, this approach, while it pre-computes answers to specific queries, it boosts performance, but it's still entirely manual. Each new question requires building another custom aggregation, creating a patchwork system that solves nothing about standardization. This is like creating cheat sheets for a specific exam question. It works for well-known problems, but fail completely when faced with new, unexpected questions. Okay, now as we've seen, each alternative fails to fully resolve the core problem. They either bypass, manually patch, shift, or restrict. What none of them do is provide a foundational universal language for OLAP that works natively with the flexible document model. This critical gap is exactly what our research addressed. Our solution introduced a foundational layer of abstraction. It represents a set of mathematical rules that define what an OLAP operation is, in pure logic, completely detached from the messy realities of document structure. It represents grammar that allows us to translate analytical intent into efficient execution. Now, our algebra begins with a set of basic operations, familiar in concept but designed for the document model. Project select help us shape and filter our data. Union let us combine results from multiple collections. And aggregate allows us to perform aggregation to measures. These are the atomic elements of our analytical language. All right. On the top of the basic vocabulary, we build a complex grammar of roll-up, and a drill down that allow navigation through level of details. Slice and dice enable focusing on specific data segments. Crucially, these are not new magic commands. They are formally defined as composition of our basic operator that can be applied across any document structure and even on a pre-computed lattice. Now, let's look at what this algebra actually delivers in practice. First, algebra universality. It means the same algebraic expression works seamlessly across any document collection, whether you're dealing with raw and processed data or pre-aggregated results. It likes having one master key that opens every single door in your data warehouse. Second, lattice acceleration. By leveraging pre-computed aggregates organized in our lattice structure, we transform complex analytical queries into simple, fast projections and selection. It is the difference between calculating your taxes manually versus having them pre-filled. The same result, dramatically less work. Third, flexibility. Because sometimes you need to explore beyond the pre-computed path, the algebra gives you the freedom to work directly with raw documents when you're doing an ad hoc analysis or when a pre-computation isn't feasible. It's your analytical safety net. And finally, portability. Here we mean that your analytical logic is no longer trapped in one database structure. The same algebraic expression can be translated across different document databases. Okay, to conclude, let us bring it all together.
دكتورة سمية ممكن عندها مشكلة في الصوت. هي وصلت للكونكلوجن متاعها.
NoSQL databases. This isn't just another tool, but a foundational layer that brings mathematical rigor to flexible data environments. The impact is clear. We can now deliver trustworthy analytics and document structure while maintaining NoSQL core advantages. All right. Thank you for your attention and your time, and I'm open to any questions you may ask.
شكرا دكتورة سمية على هذا التقديم الرائع في المداخلة الأولى في محور إعادة تصور ذكاء البيانات. في الجزء الثاني والمداخلة الثانية في نفس المحور يركز هذا الجزء على تطوير إطار عملي وموثوق لعمليات الاستخلاص والتحويل والتحميل المصممة خصيصا لقواعد البيانات الموجهة نحو الوثائق، يهدف تعزيز كفاءة تكامل البيانات وبناء مستودعات بيانات ذكية وقابلة للتوسيع. المداخلة الثانية تقدمها الدكتورة سندة بعنوان Extending ETL for NoSQL Validated Framework for Document-Oriented Data Warehousing. ستتطرق الدكتورة سندة إلى التحديات التي تواجه عمليات الاستخراج والتحويل وتقدم إطاراً معتمداً يدعم تحسين بناء مخازن البيانات الوثائقية.
Hello everyone. It's a great honor for me to participate in this year's edition of the Women in Data Science Worldwide. Today, دكتور أحلام.
دكتورة سندة موجودة؟
موجودة. presentation اشتغل. دكتورة واضح. Today we will present our work entitled Extending ETL for NoSQL Validated Framework for Document-Oriented Warehousing realized by myself. The presentation is based on our paper published at the Conference on Knowledge-Based and Intelligent Information Engineering System 2025, ranked B, where it was selected as the best paper of track knowledge-based and expert systems. The presentation is structured as follows. First, I will present the research context. Next, I will introduce NoSQL databases. After that, I will explain the proposed GUTL NoSQL approach. Finally, I will conclude the presentation. Let's start this presentation by addressing the context, which primary concern decision support system. The system consists of a set of technologies that enable the processing, validation, and presentation of data in order to assist decision makers. At the heart of these systems lies the data warehouse, which forms the foundation of most decision-making applications. According to Iman, a data warehouse is a collection of subject-oriented, integrated, non-volatile, and historical data organized to support decision-making. The feeding of a data warehouse relies on ETL processes, which it is the essential process that allows the data warehouse to be fed with extracted, transformed, and loaded data. Decision-making process rely heavily on data warehouses, which are powered by extract, transform, load systems. Traditional ETL solutions were designed for relational databases with a strict schema. However, with the emergence of big data and NoSQL systems, new challenges have appeared, such as schema flexibility, heterogeneity, and the need for scalability. Our objective is therefore to adapt ETL processes to NoSQL environment in order to ensure scalable and analytical processing. Let's first introduce the four categories of NoSQL databases used in modern data management. NoSQL systems are generally classified into four types, each designed to handle specific data structure and scalability needs: the key value database, the column database, the document database, and the graph database. Now, let's move to the type used in our work: document-oriented databases. A document-oriented database is organized around the concept of a collection, which groups a set of documents. Each document is structured as a key value pairs. Document means that values can be not only scalar or lists of reference, but also nested documents. To address the limitation of traditional ETL in NoSQL environment, we propose a new approach, ETL process scaled TETL NoSQL. To achieve this, we propose a new TETL NoSQL processes in which we have incorporated an aggregate calculation step during the transformation phase to improve analytical performance, and integrated a structure creation step during the loading phases to automatically generate and organize NoSQL schema. Our proposed TUTL NoSQL process is based on three main phases. The first phase consists of extracting data from the document-oriented database. The second phase of the ETL process involves the use of a transformation to convert source data according to the NoSQL data warehouse schema. This phase prepares the data to feed the data warehouse schema in order to populate the component of the multidimensional model. The third phase relates to loading. The first phase consists of extracting data from the document-oriented databases. These steps differ depending on the type of database used. For document-oriented databases, extraction starts by establishing a connection. The second phase is the transformation phase. This phase maps and prepares source data according to the NoSQL data warehouse schema. It includes two types of transformations: simple transformation and complex transformation. The simple transformations refer to transform that map source schema to the data warehouse schema. An example of a sample transformation is determining the date parameter according to the date dimension. The complex transformation involves calculating aggregates according to the latest modeling, one-dimensional lattice aggregation. This transformation corresponds to the one-dimensional lattice aggregation. In this transformation, each cuboid at this level is transformed into a document. The task is to calculate at each hierarchy level that is transformed into a document the possible aggregation function. Each level contains the load levels nested with the corresponding measure values. The nested attribute related to a parameter in a hierarchy must include the sample attribute that represent the value corresponding to the measure aggregation. This transformation is formalized in rule doc1. This figure shows the Python code used for calculating the aggregate of the date dimension cuboid. This code allows the calculation of the following aggregate: new cases per month and new cases per years. Complex transformation aggregate calculation on two dimensions. This transformation allows the calculation of the two-dimensional cuboid lattice. The cuboids at this level are transformed into a collection. Each combination of parameters from the two dimensions is transformed into a document in the collection containing the aggregated measure. This transformation is formalized by rule document2. The same principle is applied for levels where a number of aggregation greater than 2. After completing the transformation phase, we can now move to the final step of the process, which is the loading phase. The loading of the data warehouse in a document-oriented database is a process composed of 3 steps. The loading phase. This process begins with the import of the data structure in which the data is transformed. Then the structure is created. Finally, the process ends with loading the data into the created structure in accordance with the transformation rules. In summary, traditional ETL systems are effective for structured relational data, but face challenges when dealing with the flexible schemaless NoSQL environment. To overcome this limitation, we proposed the ETL NoSQL process based on the latest concept. The model introduces an aggregate calculation step daring transformation, involving analytical performance, structure creation step, daring loading, enabling automatic organizing of NoSQL schema. Finally, I would like to thank you for your attention.
شكرا دكتورة سندة على هذا التقديم للتحديات التي تواجه على عمليات الاستخراج والتحويل والتحميل. نمر الآن للمحور الثاني، الجيل الجديد في علوم البيانات. يعد هذا المحور الثاني من الجلسة حيث نسلط فيه الضوء على عصر الذكاء المعزز بالتقنيات وحدات معالجة الرسومات الذي يمثل مرحلة محورية في تطور علوم البيانات. تمكن هذه التقنيات من معالجة كميات ضخمة من البيانات بسرعة عالية وكفاءة متقدمة، مما يعزز أداء خوارزميات التعلم الآلي والذكاء الاصطناعي بشكل غير مسبوق. وقد فتح هذا التطور آفاق واسعة للبحث والابتكار ودعم التطبيقات التي تتطلب قدرات حسابية مكثفة سواء في التحليل أو النمذجة أو التعلم العميق. في هذا المحور تقدم لنا الدكتورة رانيا، وهي مدربة معتمدة في معهد التعلم العميق في انفيديا. أحدثت توجهات في تسريع خوارزميات علم البيانات باستخدام وحدات معالجة الرسومات، مبينة كيف يسهم هذا التطور في رفع كفاءة أداء وتحسين قدرات النمذجة والتحليل. تفضلي دكتورة رانيا.
السلام عليكم. شكرا كثيرا لكم. أنا سعيدة بالمشاركة في هذا الملتقى. So, welcome to the presentation about fundamentals of accelerated data science. This presentation serves as introduction to data science with emphasis on speed and efficiency. It's been designed for new and practicing data scientists that are looking to accelerate workflows and optimize results with the NVIDIA GPU. This presentation is organized into 3 sections. The first one is about the introduction to data science and data manipulation. The second section focuses on graph analytics, and the last one covers various machine learning tasks. Let's begin with the first section. We will explore the GPU computing and RAPIDS, which is a sort of libraries designed to enable GPU acceleration. We will understand how GPUs accelerate data processing. Along the way, we will also discuss data visualization and interoperability of GPU libraries. At its core, data science is the study of data to extract meaningful insights, powering applications such as customer segmentation, personalized recommendations, fraud detection, supply chain optimization, and predictive maintenance. In today's rapidly evolving business landscape, data science is no longer just an advantage, it's a necessity. By deeply integrating data science into operations, business can unlock their full potential and thrive in the digital economy. Data science is recognized as a multidisciplinary field that blends principles and practices from mathematics, statistics, artificial intelligence, and computer engineering to analyze large volume of data. A data scientist is responsible for tasks such as business intelligence, data mining, business analytics, predictive analytics, etc. While machine learning and analytics are vital outcomes of data science, non-analytical tasks are equally important to ensure the meaningful outcomes. Data preparation, like ETL process, plays a foundational role in data science workflow. It's the quality of the input data that ultimately determines the reliability and the value of the outcomes. This part of the workflow can take more than 40% of data scientists' time. Proper ETL ensures so that raw data from various sources are collected, cleaned, and made usable for analysis. You may be surprised to learn that the biggest challenge in data science today is not centered around the analysis techniques themselves. Modern data science faces challenges like the rapidly growing and varied data set, slow CPU performance due to limited parallel processing, and the complex software management. To put things into perspective, let's walk through a day in the life of a data scientist. Due to the large size of data set, the processing can take significant amount of time to complete. When working with new data sets, it's common to forget a step or make a small mistake. This not only disrupts productivity but also limits opportunities for exploration and experimentation. To overcome this, we need workflows that are fast, efficient, and support iterative experimentation. With accelerating computing workflow, data scientists are able to achieve high productivity, allowing them to focus on meaningful tasks. The result is to have a good result with reduced time. Accelerated can be achieved by leveraging specialized hardware like the GPU. By adopting GPU acceleration, we can ensure the exponential growth and communicating performance. Now, GPU computing delivers more than 1,000 times the performance of single-threaded computing. Let's take a simple example involving structured data. Structured data is defined by having a predefined format or schema. This is represented by the use of data frames. A data frame consists of columns and rows, which why there is often referred to as tabular data. Each column represents a feature, property, or dimension, while each row corresponds to an individual record or instance. Within the computer's memory, this data is stored as a matrix. There is several ways to interact with a GPU, depending on your experience and goals. The most used one is the QDF, or the first one is the QDF. CUDA data frame is a GPU accelerated Python library for loading, joining, aggregating, filtering, and manipulating data using a data frame API. For data sets that don't fit into a single GPU, we need to distributed computing to scale data processing across a cluster computing nodes that work together as a single system. By the use of some libraries like Flask, we can harness the power of multiple GPUs using the same system where each GPU acts as individual workers. This approach is a powerful solution for massive data sets, enabling scalability and performance. In modern data science, we have a variety of tools for data manipulating. Selecting the right one depends on the size of the data, used hardware, and the performance requirement. The next thing we can do with data visualization is the process of representing the data graphically to extract patterns. We can use common chart types such as scatter plots, line charts, or bar charts. This is an excellent opportunity to discuss the evolution of GPU-accelerated data science. While GPU acceleration itself is not new, NVIDIA has progressively developed optimizations for specific processes over time. However, this application often requires specific data format for different steps, leading to frequent data coupling and conversation through the pipeline. Unfortunately, these extra operations can reduce or negate the performance gains achieved from GPU acceleration. By expanding functionality within Rapids, we can minimize or even eliminate the data transfers across systems. Ideally, all processes would utilize a shared data memory format, removing overhead caused by system communication and ensuring a seamless high-performance workflow. Rapids ensures strong interoperability with QPython for array computation using CUDA and Q deep learning, which are widely adopted in most deep learning frameworks. To summarize, Rapids is a suite of GPU-accelerated libraries designed to speed up the data science workflows on the GPU. Latestly, when working with GPUs, there is several key considerations to ensure optimal performance. Use columnar operation whether possible for faster computations and to keep data on the GPU as much as possible. Let's move to the section 2. We will start with a brief introduction on graph and graph data. We will then discuss some popular graph algorithms and use cases. A graph is a mathematical structure used to represent the relationships between objects. It consists of two fundamental elements, which are a node and edge. Nodes, edge, and graph can be distinguished by their unique properties. A graph can be undirected, directed, or weighted graph. There are few fundamental concepts that are crucial for understanding the structure and the relationships within a graph, which are, for example, the degree to help us measure the node importance or connectivity. The neighborhood also help us to explore the local structure. By using graph theory and graph-based analytics, researchers can uncover complex relationships, optimize processes, and gain deeper insight into the system they study. A knowledge graph is also a powerful data structure that represents a network of real-world entities and illustrates the relationships between them. So let's look at some ways to represent or visualize graph data. Here we are looking at the adjacency matrix across the rows and columns. We can also use other values to represent edges or edge properties for weighted graph. Here we are looking at the degree matrix that summarizes the number of connections each unique node has. When we combine the two, we have the Laplacian matrix. One such example is the shortest path algorithm. Given a graph on a source node ID, the algorithm calculates the distance of all reachable nodes. This can be used for networks, logistics, communications, and network analysis. Centrality is a fundamental concept in graph theory and network analysis that measures the importance or the influence of node. Also, we have 4 types of centralities, which are the degree centrality, the closeness centrality, the betweenness centrality, and the rank centrality. Network X is a popular library that provides functionalities for working with complex networks and graph structures. It can be accelerated with GPUs using libraries that CUDA graph. Depending on the algorithm and the graph size, speed up can range from 10 times to 500 times. Network X graph, Q graph, allows data scientists to benefit from GPU accelerations in existing Network X workflows without modifying the code. These are some examples of the use of Network X. Now, let's move to the last sections, which is the section 3. We will start by introducing the fundamentals of machine learning. Next, We will dive into real-world application, examining practical use case of machine learning algorithms. We'll then explore some of the most widely used machine learning algorithms. By integrating machine learning into the data science, organization can uncover deeper insights, make more accurate predictions, and drive innovation across diverse industries. Traditionally, programming relies on rules-based approach. Machine learning takes fundamentally different approaches compared to traditional programming. Machine learning refers to the systematic approach of learning from data which can be characterized into various types. Supervised learning, the learning algorithm is provided with both input data and the corresponding desired output. The category of machine learning is unsupervised learning, where the learning algorithm is not provided with labeled data. Let's explore an example data set to better understand key machine learning concepts. Our dataset consists of 3 columns, often referred to as features, dimensions, properties, or attributes. Each row represents a record or observation. The features could represent financial metrics like income, credit score, or loan eligibility. Let's explore also an example of classification problem using a single feature to predict class membership. For this example, we use logistic regression, a widely used algorithm for binary classification. We train the logistic regression model on our data set and plot the decision boundary to visualize how model classified data points. In these visualization points, to the left of the boundary are classified as class 0, and points to the right of the boundary are classified as class 1. However, our visualization also reveals classification errors where some points fall on the wrong sides. We can enhance our classification model by incorporating more parameters and training it with additional features. The same data can be utilized for multiple machine learning tasks. Let's explore how we can apply clustering, another key machine learning technique, to our data set. Clustering is a supervised learning method that uncovers inherent patterns and data without requiring priorly labeled data. It groups some other data points together based on shared characteristics. A well-known algorithm is the K-mean clustering. Inference is when a trained machine learning model is used to make, of course, prediction on new unseen data. At this point, the model can fix parameters remain unchanged. Inference is often integrated into application to deliver real-time or batch predictions. Returning to our simple example, model inference refers to the process of passing new records into the trained model to predict either class IDs or cluster IDs. In a changing world, machine learning models can lose accuracy over time due to data drift, which is a phenomenon caused by evolving data usage behavior and environment changes. To stay effective, models should be monitored and automatically retrained as needed. Using machine learning to solve the problem begins with framing it as a task. A structured machine learning workflow ensures the development of efficient and reliable models. Here's are the stages. Gather relevant data from multiple sources, clean, transform, and prepare data for analysis. Then analyze the data to identify patterns, trends, and potential biases. Next, to select, create, and transform features to enhance the model performance. Then to choose the most suitable algorithm based on the problem is to train neither the selected model using the prepared data set, assess the performance using relevant metrics, and finally is to integrate the trained model into production environment. Each stage is crucial for building a robust and scalable machine learning solution. So, once the features are prepared, we move to model training. The process starts with choosing a suitable model and its configuration. Most machine learning frameworks provide pre-built models with simple inference handling. I can pass these. So let's explore some key algorithms. We have some examples of classification with the Kainan, with the logistic regression, the decision tree. I choose the most famous one or the most used one, which is the decision tree. Decision trees are popular choice in machine learning due to the robustness of outliers, ability to handle categorical variables, and lack of assumption about data distribution. A decision tree starts at the root node, where the data is recursively split into subsets based on chosen criterion. Despite their efficiency, decision tree can be computationally intensive and prone to overfitting, meaning they may capture noise instead of true patterns. This issue is commonly addressed using ensemble learning, where multiple decision trees are combined to enhance model performance and regression. I can pass that. Okay. So, boosting is a sequential ensemble method where models are trained iteratively, where each model focuses on collecting the error of its predecessors, improving overall performance. Once training is complete, evaluating models' performance is crucial in determining its readiness for production. A model can underfit when it's faced to learn meaningful patterns, and the model can overfit when it learns too many granular details and noise from the training data. Beyond achieving high accuracy, another critical consideration is machine learning models is processing time. So, more complex models generally takes longer to generate outputs, leading to a higher latency. In production environments, low latency is essential as applications often require fast, near real-time predictions. In addition to Q data frame for data manipulation and QGraph for graph analytics, Rapids offer libraries specially tailored from machine learning. One such library is QML, CUDA Machine Learning. It's a GPU-accelerated machine learning library designed to harness the power of CUDA for low-level computational optimization, delivering significant speed improvement for end-to-end machine learning model deployment. As an example, XGBoost is a high-performance machine learning library that implements gradient boosting. It's available with the use of QML. Here, for example, okay, for the deployment, NVIDIA Training Interface Server Triton is an open source platform designed to streamline AI inferencing and optimize model deployment in production environments. With NVIDIA Triton, AI inference becomes scalable, efficient, and easily deployable, making it an ideal solution for high-performance AI. And as you can see, this is an example of the use Triton for as a model analyzer report. The entire machine learning workflow can be GPU accelerated. It facilitates the higher data quality and quantity that directly impact the model performance. And here we have some examples. So machine learning is not one-time process. It's an ongoing cycle of monitoring, refining, and improving models. Even after deployment, the data flywheel leverages newly collected data to enhance model effectiveness and trigger a training model when necessary. And thank you for your attention.
Thank you دكتورة رانيا على هذا التقديم المميز. السادة والسيدات الحضور، أود أن أشارككم بعض ما تم التطرق إليه اليوم. قدمت الدكتورة سمية أولاً رؤية بحثية متقدمة حول كيفية نقل قدرات التحليل المتعددة الأبعاد أولى إلى قواعد البيانات الوثائقية، وتم خلال المداخلة عرض جبر شامل يسمح بتمكين التحليل الهيكلي حتى في غياب البنى التقليدية، مما يفتح المجال لتطبيقات ذكاء البيانات على بيانات غير منظمة وموزعة. تطرقت بعدها الدكتورة سندا إلى التحديات التي تواجه عمليات الاستخراج والتحويل والتحميل عند التعامل مع البيانات الوثائقية، وقدمت إطاراً معتمداً يدعم تحسين بناء مخازن البيانات الوثائقية مع ضمان جودة البيانات وقابلية التطوير. واستعرضت في المداخلة الأخيرة الدكتورة رانيا أحدث الاتجاهات في تسريع خوارزميات علم البيانات باستخدام معالجات الرسومات، وتناولت كيف يسهم هذا التسريع في تحسين أداء خوارزميات الذكاء الاصطناعي، تمكين معالجة البيانات عالية الكثافة، دعم تطبيقات التعلم العميق في زمن الحقيقي، مما يرسخ دخولنا فعليا في عصر ذكاء عالي الأداء. وفي ختام هذه الجلسة نجدد التزامنا في ويتس بدعم حضور المرأة في مجال علم البيانات وتسليط الضوء على خبراتها وأنجازاتها البحثية. لقد أثبتت المداخلات اليوم أن مستقبل البيانات يتجه نحو مزيد من المرونة مع قواعد البيانات NoSQL، مزيد من القوة مع الحوسبة المسرعة بالGPU، ومزيد من الابتكار عبر توسيع الأدوات التقليدية لتتلائم مع عصر البيانات غير المهيكلة. نشكر الحاضرين ونثمن مشاركة المتحدثات المتميزات اللواتي قدمنا محتوى غني يعكس الريادة والتميز في هذا المجال مع أطيب التمنيات والتوفيق. شكرا جزيلا لحضوركم وشكرا للاستماع.